So now we will be discussing about the scattering of light, as I said in the last time. So what is this scattering? Scattering is the process of absorption and then the re-emission of light energy. So whatever be the particle, whether it's a water molecule, whether it's a dust particle, the process of absorbing the light energy first and then re-emitting the light energy is known as scattering. The intensity of the scattered light is proportional to the fourth power of the wavelength, but inversely proportional. That is to say that greater the wavelength, smaller will be the scattering, and smaller the wavelength, greater will be the scattering. Intensity of the scattered light is inversely proportional to the fourth power of the wavelength. Now we know that lambda blue is 400 nanometers and lambda red is 800 nanometers. So we can see that red has got a greater wavelength than blue. So the intensity of the scattered light for red will be less than that of blue. Red has this lambda equal to 800 nanometers. That means it has a greater wavelength than blue. Greater wavelength, a greater quantity in denominator, so a smaller quantity in numerator. So red light is scattered less than that of blue light. Now we can also see that red light has a wavelength which is almost 2 times that of blue light. So if I put a figure of 2 here, that means the intensity is proportional to 1 by 2 to the power 4, which is almost 16. That means blue light is scattered 16 times more than that of red light. One of the essential criteria for scattering to take place is that the size of the scattering particle must be smaller than the wavelength of incident light. So whatever is the particle, whether it's a cloud, water molecule or a dust particle in the atmosphere, that particular particle must have a size smaller than the wavelength of the incident light for scattering to take place. If the wavelength, the size of the particle is greater than the wavelength, then the particle will scatter all the different colors, whether it's violet, whether it's green or red, to the same extent. In that case, this law of scattering won't hold anymore. And we need to remember one thing, that as we said in the definition, that scattering is the process of absorption and then re-emission of the light energy. Re-emission does not change the wavelength. So if a certain dust particle absorbs wavelength corresponding to 500 nanometers, when it will re-emit that light energy after absorption, it will still remain at the wavelength of 500 nanometers. It shall not change. So the 3 key points are: scattering is the process of absorption and re-emission, both. Number 2 is that for the scattering to take place, this particle must have dimensions smaller than the wavelength of light. And number 3, re-emission will not cause any change in the wavelength of the light. Now we will come into the various applications of scattering, like why the sun is red in color during sunrise and sunset, or why the sky is blue in color during day or after sunset. Similarly, what would be the color of the sky in the absence of an atmosphere, and so on. So this is the first application, the case of red sun at sunrise and sunset. This is the earth and this is the sun. Actually the sun is much bigger, but this is for the clarity of the diagrams we have drawn in this manner. So this is the sun, and suppose these small dots that you can see are the different dust particles and molecules present in the atmosphere of the earth. And an observer is viewing the sun during sunset. Now the sun emits wavelengths in the entire visible spectrum. It will emit blue light, green light, yellow light, red light, and so on. We have taken the 2 ends of the visible spectrum. So the blue light is incident upon the atmosphere and also the red light. As you can see with the small arrows, the blue light gets scattered more. And the reason is the law of scattering. It has a smaller wavelength, so the intensity of scattering is higher. Excuse me. So the wavelength of blue light is smaller, so the intensity is higher. Therefore you can see that blue light is scattered more, whereas red light has got a longer wavelength and it's scattered least, and it manages to reach the eye of the observer. So the observer will see a red sun, though the sun emits light in all the wavelength region. And it is for the same reason, the reason that red light can travel a greater distance without getting scattered, it is used in danger signals. In the various danger signals, in the various indicators, whether it's of car or aeroplanes, you will find that the light is always red in color. The reason is that red light can penetrate a longer distance. It can travel a greater distance through atmosphere without being substantially scattered. That is the reason for using red light in the danger signals and indicators. Now, why is the sky blue in color? Well, this is the position of the sun during sunrise or sunset. Now, during noon or during any time of the day, generally the sun is somewhere here. It's actually overhead, and from there the sunlight travels in straight line path to the earth. Traveling in straight line path means that it has to penetrate a smaller distance of the atmosphere. When the sun is somewhere here and it's traveling to this person, and this is the atmosphere, so it has to travel this much distance of the atmosphere during sunrise and sunset. So since it is traveling a longer distance of the atmosphere, the chance of the blue light getting scattered away is also higher. But during noon or during daytime, it is traveling only a smaller distance of the atmosphere compared to this. So since it is traveling a very small distance, the wavelength of the light, especially the blue region, does not get substantially scattered, and we see almost all the 7 light to the same extent. That is the region the sun generally looks white when viewed during daytime or when viewed at noon. But apart from the sun, like if you look directly at the sun or in the region around the sun in the sky, you will see that it is white in color. But if you see in the other regions of the sky, say the direction opposite to the sun, you will still find that the region is blue. And that is again due to the scattering. Because these regions of the atmosphere, the light is traveling a longer distance, is substantially getting scattered, and you are seeing a blue color of the sky. The red light is traveling unscattered. Red light does not scatter much, so it travels unscattered and passes outside the atmosphere, outside of our field of vision. But the blue light, it gets scattered within the atmosphere, and so we get to see the blue color of the sky. Now, what would be the color of the sky if there were no atmosphere? So, for a moment, suppose that you are standing on moon, and somewhere here is the sun, and you are looking at sun. And it's a well-known fact that moon does not have an atmosphere. So, what would be the color of the sky as seen from moon? If you have ever seen pictures on the internet, the sky is pitch black. What's the reason? In moon, what happens is that the light from the sun, light always travels in straight line according to the rectilinear propagation. So the region in which the sun is present in the sky, that region is brightly lit. But all the other regions, the regions in which the sun is not present, they are black. And the reason is that though the light from the sun is reaching these directions as well, light travels in all directions equally, since there is no atmosphere, there is no dust particle or water molecule present to scatter these rays of sun and produce that bluish hue that we can see on earth. So in moon or in any region where there is no atmosphere, you will find that the sky is black in all other directions, but only in the direction in which the sun is present, you can see the light of the sun, and thus the sun is visible. Finally, we shall delve into this topic, that why clouds are white in color. So why are clouds white in color? Well, generally what happens that the molecules which are present inside cloud, they have a size which is greater than the wavelength of the incident light. And as we had said that for scattering to take place, the size of the particle, the scattering particle, must be less than the wavelength of light. Since for clouds the size of the particles is greater than the wavelength of light, they scatter all the colors in the visible spectrum to the same extent. They do not scatter blue the most and red the least. Since they scatter all the wavelengths to the same extent, all of them reach our eye in a similar manner at the same time, and it appears to us that the clouds are white in color. So that was all about the scattering of light. What are the different properties to be fulfilled for scattering to take place, and what are the applications of scattering. That's all about this chapter 6, the chapter spectrum. I hope that all these videos, they're clear to you and that you can really understand the concept, the ideas, the applications which we were talking about, so on. Next time when I make a video, it will be on a different chapter. Thank you. Have a good day.